Lesson 3, f of x, recognizing functions and function families. This is going to be a 2-day lesson. Let's begin with day 1. Warm up. Identify the domain and range of the relation described by each set of ordered pairs. Write an equation using the variables x and y that could map the domain to the range. Number 1. Your domain are your x values. So we have -3, -2, -1, 0, and 1. Your range are all your y values. We have -6, -4, -2, 0, and 2. You want to look at your domain. Remember, your domain is your independent, and what's going to happen to the domain so that you get your output as your range. You might could guess that you are multiplying your domain by -2. So we can write the equation y equals -2x. Whatever my x value is, I'm multiplying it by -2 to get my output, to get my range. Number 2, my domain is -3, -2, -1, 0, 1, and 2. My range is 9, 4, 1, 0, and it looks like 1 and 4. Again, those are repeating, and I really do not need to list them again. It's not wrong if I do. What is happening to the domain to get the output of the range? It looks like we are squaring the numbers. If I take -3, the first number, and raise it to the second power, -3 times -3 gives me a +9. So here, y equals x squared. Number 3, my domain is -3, -2, -1, 0, 1, and 2. My range, which are your y values, are 3, 2, 1, 0, -1, -2. And if you look at them stacked up here, you notice like the first one, one's negative, one's positive, one's negative, one's positive. So there's a pattern here. It looks like the range is turning into its opposite. So there my equation could be y equals -x, the opposite of x. Our learning goals for this lesson, or the 2-day lesson: define a function as a relation that assigns each element of the domain to exactly one element of the range. This is a key definition of function right here. Write that down in your notebook. A function is a relation that assigns each element of the domain to exactly one element of the range. And remember, I also said the domain does not repeat. Second learning goal, write equation using functional notation. So functional notation is like your f of x, g of x. That's functional notation. And all that really means is y. It's your output. Recognize multiple representations of functions. Determine and recognize characteristics of functions. Determine and recognize characteristics of function families. This is a big lesson. Key terms. So a lot of definitions we're going to go over today. Some we've already mentioned. We've mentioned discrete graph and how it's broken up in pieces. We've mentioned a continuous graph, how it's just a continuous one-piece graph. We've mentioned linear functions, how they are straight lines. Exponential functions we haven't discussed yet. And quadratic functions have your U-shaped graph, whether it's going up or going down. You may have a smiley face or a frowny face. A lot of new things we're going to learn about. You have sorted graphs by their graphical behaviors. How can you describe the common characteristics of graphs of the functions? Getting started, odd one out. Which of the graphs shown does not belong with the others? Explain your reasoning. So we got graph A, graph B, graph C, and graph D. Which of the graphs shown does not belong with the others? Explain your reasoning. A lot of things we could say about these graphs. I've got two linear graphs. B and D are clearly both lines. But the difference is one is a function and one is not. A is a type of exponential graph, and C is a quadratic graph. First activity, functions and non-functions. A relation can be represented the following ways. So a relation, you may want to jot this down in a notebook, can be ordered pairs or an equation. Both of these are relations, and we're going to identify whether this relation is a function. A relation, side note here, is the mapping between a set of input values, called the domain, and a set of output values, called the range. A relation can be represented in the following ways. You can verbalize your relation, the relationship between students in your school, and each student's birthday. You can show a mapping of a relation. You've got your domain in one bubble and your range in another bubble. Continuing with relations. A relation can be represented with a graph. A relation can be represented with a table. So a relation can be represented 6 ways: ordered pairs, equation, verbally, mapping, a graph, and a table. All of these are relations. We're going to study and find out if these relations are a function. Sometimes they're not. A function. A function is a relation that assigns to each element of the domain exactly one element of the range. Functions can be represented in a number of ways. Analyze the relation represented as a table. Is the relationship a function? Explain your reasoning. Focus in on the domain. Let's look at the domain. -1, 2, 5, 6, and 7. Those are all different. If you notice, I didn't even look at the range. I focused in on the domain. To be a function, every number in the domain has to be different. It cannot repeat. So this is a function. If you notice, the range repeats here, but that's okay. The range can repeat. The domain cannot repeat. Let's look at the mapping. Analyze the relationship represented as a mapping. Is the relation a function? Explain your reasoning. Again, we're going to look at the domain. It might be easier to understand this mapping if they were written as ordered pairs. 1 maps to 2. 4 maps to 5. 4 again maps to -5. Notice anything? That's right. My domain right here is repeating itself. That means we don't have a function here. Please remember, to be a function, every value in the domain must be different. This one, not a function. Let's look at a verbal situation. Analyze the relation represented verbally. Is the relationship a function? Explain your reasoning. The relation between students in your school and each student's birthday. Yes, this would be a function. Every student in our school has one and only one birthday. So we would say, yes, this is a function. You can look at an equation representing a function using functional notation. Let's look at the relationship between an equation and functional notation. Consider this scenario. U.S. shirts cost $8 per shirt plus a one-time charge of $15 to set up a t-shirt design. Here's our equation. The equation y equals 8x plus 15 can be written to model the situation. The independent variable x represents the number of shirts ordered, and the dependent variable y represents the total cost in the order of dollars. Look down here at the side note. Function notation is a way of representing functions algebraically. The function notation f of x is read f of x and indicates that x is the independent variable. So in other words, whatever you have inside your parentheses, sometimes it's x, sometimes it's a different letter, is your independent variable. The letter on the outside represents your dependent variable. This is a function because for each number of shirts ordered, independent value, there is exactly one total cost, a dependent value, associated with it. Because this relation is a function, you can write y equals 8x plus 15 in functional notation. So notice your f of x. Notice the x inside. That is your independent value. It is over here. F of x is the name of the function. F of x, the whole f of x expression or phrase stands for y. The cost defined by f is the function of f, defined as the number of shirts ordered. You can write a function in a number of different ways. You could write the t-shirt cost of function as capital C and in parentheses put s. C of s equals 8 times s plus 15, where the cost defined as C is a function of s, the number of shirts ordered. Let's look at our side note. If f is a function and x is the element, its domain, then f of x denotes the output of the f corresponding to the input of x. Number 4, consider the U.S. shirts cost. C of s equals 8s plus 15. What expression in the function represents the domain of the function? That's right. S represents the domain of the function. What about the range of the function? Everything listed on this side equals, remember what I said? Y. Y represents our range. So C of s represents y, so it equals 8s plus 15, All of that is your range, your output, your dependent. Describe the possible domain and range for this situation. The domain represents the number of t-shirts. Maybe I don't buy any t-shirts. Then I'd start with 0. Maybe I buy 1 t-shirt, 2 t-shirts, 3 t-shirts, and so forth. So you see, this is a set of whole numbers. My range, based on if I don't purchase any t-shirts, is still that $15 setup fee. If I buy 1 t-shirt, then it's $15 plus 8, which gives me $23, and so forth. The vertical line test, this might be something new to determine whether you have a function, is a visual method used to determine whether a relation is represented as a graph. To apply the vertical line test, consider all vertical lines that could be drawn on the graph of a relation. If any of the if you look at the green line in both examples, you can see that this is a function. This green line represents our vertical line test. It's only touching one point at a time. If that vertical line continued to move, it would still only touch one point at a time. That's what makes it a function. Here, in this graph, it's touching at 2 points. This is indicating that our domain is repeating. This is not a function. So imagine holding your pencil or pen and using it as a vertical line test. Now we've talked about a discrete graph. A discrete graph, over here on our side note, is a graph of isolated points. A continuous graph is a graph of points that are connected by a line or a smooth curve on the graph. Continuous graphs have no breaks. The vertical line test applies for both discrete and continuous graphs. How can you determine if a relation represented as a set of ordered pairs is a function? Explain your reasoning. Ordered pairs is probably the easiest one that you can look at. If we take an example here, and I'm just going to make up some numbers. All we need to do is look at the domain. 4, 3, 1. They are all unique. They're all different. This is a function. A function is determined or based on the domain. If the domain is all different, it is a function. If at any point the domain repeats, it is not a function. Let's look at an example of not a function. Notice what happened. These 3's are repeating, not a function. Number 7, how can you determine if a relation represented as an equation is a function? Explain your answer. An equation represents a function when you can solve for y and get one y value for that given x. Let's go over a few functions that are a bit confusing. You've got y equals x. Y equals x is a function. It is a linear function. Y equals x squared is a function. It is a quadratic function. Y equals the absolute value of x. It is your v-shaped function. Y equals some number with an exponent of x. This is called exponential. It may exponentially increase or it may exponentially decrease. But all of these are examples of functions, and we're going to discover these today. Number 8, determine which relation represents function. If the relation is not a function, state why not. Number 8. Number 8, part A, is a function. This is one of the exponential functions that was described. This is a function. For any value that I put in for x, I'm going to get a different and unique range. Part B, for every house, there is one and only street address. This is also a function. Every house is going to have only one street address. Part C, you have a table. I'm going to focus in on my range, my domain. Notice my 2 zeros, not a function. Did I say anything about the range? I don't need to even look at the range. Just look at the domain. Part D, we're going to look at the mapping. Determine which relations represent functions. If the relationship is not a function, state why not. Again, look at the domain. The mapping, written as an ordered pair, is a lot easier to analyze. And I could stop there. What do you notice? The 2 is repeating. So if the 2 is repeating, this relation is not a function. Part E, let's look at a set of ordered pairs. Focus in on the domain. I've got -7, -5, 2, and 3. All of those are different. This is a function. Part F, we have a graph. Look at these vertical lines. These vertical lines can indicate our vertical line test. Notice that these pink lines are only going through one point at a time. Think about moving your pencil across the graph, and that pencil is only touching one point at a time as it moves. This is a function. That vertical line test is indicating that your domain is not repeating. Number 9. Analyze 3 graphs Judy grouped together in the previous lesson. Are the graphs sheet grouped functions? So let's recall back to our graphs, D, K, and O. If I did my vertical line test for D, what happened? I hit 2 points. Remember, you can only hit 1 point at a time when you move your pencil or pen across your graph. Same thing for K. I'm hitting 2 points. D and K are not functions. Look at this one. This is a straight line, but this straight line is hitting lots of domain points. So all 3 of these are not functions. The domain is repeating in every single one of these graphs. Number 10, use the vertical line test to sort the graphs in the previous lesson into 2 groups. Functions, non-functions. Record your results by writing the letters of each graph in the appropriate column in the table below. Pause the video, find your graphs, and sort them. Put the letters of the graph in the appropriate box. The functions you should have come up with from the previous lesson, from lesson 2, should be graph A, graph B, graph C, graph E, graph F, graph G, graph H, graph I, graph J, M, N, P, Q, R, and S. And just like we realized with the previous question, the only ones that are not functions are the ones Judy picked, D, K, and O. Those are not functions. But all the other graphs, no matter what different characteristics they had, they passed the vertical line test. They are all functions. We're going to pick up with this lesson in the next video.